In this lesson, we are going to talk about the average and the instantaneous rates of change in calculus. And if you are a random passerby on the internet and you want to print a sheet that you can use to follow along and take notes, then you can go to bit.ly/AROC, average rate of change, instantaneous rate of change. So AROC, and you can print the PDF that I'm using to fill in the blanks here. So let's start by defining a rate of change. And in calculus, you will see rates of change quite a bit, and it is always a reference to slope in some capacity. You have two types of rates of change. You have the average rate of change, which is the slope measured over, I should put this on one line, it's the slope measured over an interval, and the average rate of change is found by using the old-fashioned Algebra 1 slope. And so I want to talk about two different ways that you could find the average rate of change. And the first one is the generic way that you already are aware of. And that is if we have 2 points and we don't know what these coordinates are. So I'm going to call this first one be point A. And if the x coordinate is A, I'm going to call the y coordinate f of A. I suppose I should define this function as f of x over here as well. And I'm just going to call this point the ordered pair B, f of B. And if you want the average rate of change, that is the slope from point A to point B, that would simply be f of B minus f of A over B minus A. The other way we can do this is it's the same thing, but with a slightly different notation. Is I'm going to start with this point, and instead of calling it A f of A, I'm going to call that point x f of x, where my x coordinate is starting here. And this other point over here, instead of defining that point directly like I did as b f of b over here, I'm instead going to call the distance between those two h. And if this point is at an x coordinate of h, then over here I am at an x coordinate of x plus h, which would make this ordered pair x plus h and f of x plus h. Then when I find the slope between those 2 points, that slope would be f of x plus h, or change in y minus f of x, all over. And x minus x will be x plus h minus x, which ends up being f of x plus h minus f of x, all divided by just an h. The x's will subtract out in that denominator. And that fraction on the right side is a very common fraction in calculus. You probably had some exposure to it in pre-calculus, but it is nothing more than finding the slope between 2 points. So now we're going to look at those two things, and the word we use to describe those two things, how vague was that? The word we use to describe those fractions that find slope is the difference quotient. That is the fraction that measures the average rate of change, and the numerator and denominator in a difference quotient, that is not what I meant to do. The numerator and denominator in a difference quotient each contain the subtraction or the difference of two terms. And if you look at these two examples back here, the first one is explicitly a difference quotient. We have something minus something divided by something minus something. The end result of this one in green doesn't look like a difference quotient because the denominator cleaned up, but we do, however, still refer to this f of x plus h minus f of x over h as a difference quotient because of where it originated. It did originate as a change in y over change in x, so it still is considered a difference quotient. All right, so we have an average rate of change. We also have something called the instantaneous rate of change. And the instantaneous rate of change is the slope measured at a single point. And the most common way of measuring that is by using derivatives, which come from limits, which come from the average rate of change. And so I'll show you the connection from average rate of change to instantaneous rate of change in a minute. But first, a little bit of notation. The notation for the instantaneous rate of change of f of x at x equals a is denoted as f prime of a. And this represents the slope of the line tangent to f of x at x equals a. So if we have a graph, and let's just call this f of x, what we're really trying to do is find the slope at a single point, and that becomes problematic because all throughout your early high school life, you learn that to get slope, you have to have 2 points to measure your change in y over change in x. If you just have a single point, it's hard to measure that change. And so we have to use a little bit of hocus pocus with limits to make that happen. But the slope of that tangent does represent the slope of the curve at that point. And you could think of it like we're getting a really strong, that is not at all what I meant to do. You could look at it as if we are getting an extremely strong microscope, and we're going to zoom in ever so close, itty bitty zoom in really, really, really close, and keep getting closer and closer and closer. And eventually, if you get close enough, even though we can tell from a distance that there is some curvature to this f of x, if you get close enough, it has the appearance of a line, and it's the slope of that supposed line that we are interested in. So it's kind of like looking at the surface of the earth. It looks flat because we're so close to it, but we know it's curved. Same thing with the slope of a tangent line. It represents the slope of that zoomed in section of the curve, and that is our instantaneous rate of change. Okay, so let's talk about instantaneous rates of change and how we can estimate rates of change from a table. And so we have a table of values here. We do have let me move my head. We do have a differentiable function, and anytime I see that, I'm going to automatically make a note to myself that the function is also continuous because of that differentiability. And we're going to use the data in the table to answer these following questions. Find the average rate of change of f on the interval 2 to 8. And this is algebra 1. This is not anything new. So f of 8 minus f of 2 over 8 minus 2. And that would be f of 8 is 13. F of 2 is 5 over 8 minus 2, which would reduce to 13 minus 5 is 8, 8 minus 2 is 6, which then reduces to 4/3. There is your average rate of change. That should have been ridiculously easy. I want to make 2 quick points. In AP Calculus, when you are finding the average rate of change from a set of data like this, you absolutely must include the difference quotient in either one of these 2 forms. You should have the ability to jump straight to 8/6 or 4/3, but we want to see that difference quotient, that computation where you are subtracting y's over subtracting x's. So keep in mind that we want to see that. B and C gets a little bit different though, because we want to estimate f prime of 5, and we don't have that information. We don't have information on 5. I want to estimate the slope of the tangent at x equals 5. And what we do here is something called a symmetric derivative, or like a symmetric slope type thing. So to illustrate how this works and how we can estimate f prime of 5, I'm going to draw just a random function. I'll call this g of x because I don't want you to get confused with the f of x here. This is just randomly drawn. And let's just say I wanted to estimate the slope of this tangent. I want to estimate that slope right there. Well, what I could do, since I don't have any other method they'll say I don't have a method to get that actual answer. What I could do is from this point, from my point of tangency, I can move a little bit left and I can move a little bit right. And instead of finding the slope at that point, I could find the slope of the secant. I could find the average rate of change of the 2 slopes on each side. And if I find that average rate of change, if I move just to the left and just to the right, you'll see that that average rate of change is really close to the instantaneous rate of change. Now, it's not going to be exact, but it is an approximation. And that's what I'm going to do here. So on problems like this, you must use the data in the table. You're not allowed to create your own information by looking at the trends of the x's and y's here. 5 falls between 4 and 6. So if I want to estimate f prime of 5, that instantaneous rate of change, the best we can do with what we have, would be approximately the average rate of change from 4 to 6. We'll sandwich that point, and we'll find the slope from 4 to 6, which ends up being 7 minus 4 divided by 6 minus 7 minus 3 divided by 6 minus 4, which is 4 divided by 2, which is 2. A couple of notes here. We are doing an approximation, so make sure you write approximately equal to. However, once I did the difference quotient, these other things are equal. And once again, you want to show the computations, and I put it in the question this time, but be certain to show the difference quotients. Those are important. We want to actually have that on paper. Then we have another one that's very similar. We have f prime of 4. And the only thing that makes this one a little bit different than B is that 4 is actually in the table. I still prefer to sandwich that point. I'm going to go a little bit to the left and a little bit to the right. And I prefer to say f prime of 4 is approximately, that's messed up 4, is approximately f of 6 minus f of 2 over 6 minus 2, which then is 7 minus 5 over 6 minus 2, which is 2 over 4, which is 1/2. That's what I prefer to do. Now, it is also acceptable that if the point you are interested in is actually on the table, you could find the average rate of change from 2 to 4 or from 4 to 6. So, or we could say f prime of 4 is approximately f of 6 minus f of 4 over 6 minus 4. That looks like a 9. Or you could say it's approximately, I'm being lazy here, f of 4 minus f of 2 over 4 minus 2. So both of those would be acceptable. I have not seen one like that on the AP exam in a long time. They did a long time ago, ask a question kind of like that, and they accepted all 3 answers. I still prefer to sandwich the point. Lately, it seems that every time they ask the question, they give you a point, like in not part B, where that x coordinate in question is not explicitly given in the table. Okay, so this gets us to the last part of this video. Yes, this is the last part. Last part of this video where we're going to talk about the instantaneous rate of change and how we can use limits starting with the average rate of change and turn the average rate of change into the instantaneous rate of change. So visually, what we're trying to get, I'm trying to approximate f prime of 1, the slope at x equals 1. I put the point here. The function is x squared minus 3x minus 1. I want to approximate the measure of that slope, but I'm going to start with the average rate of change. We're just going to pick any other, we'll just have a random average rate of change like so, and we pick another point over here. We'll just call that point x. This is obviously 1 here. And what we do is we start with the average rate of change between 2 points, and then we use limits to change the length of the interval between the points to 0. So we start with an average rate of change, then use limits to reduce the distance between those 2 points to 0. And I'm going to illustrate how that works in just a second. I'm going to pull up my Geometry Sketchpad program here, and we'll look at it right here. So right here we have our parabola, the x squared minus 3x minus 1, I think is what it was. I have the green line illustrating the instantaneous rate of change at 1. So there's my point. Then I have this blue line, which represents some secant, and I can find the average rate of change between this point up here, which is randomly defined, randomly found. I just called it x, and this point 1. And so what happens with this average rate of change? What happens with this secant? As that x, if I take this x point right here, and I drag that point closer and closer to 1. If I move x and I reduce that interval from 1 to x, as that length reduces to 0, as x gets closer and closer to 1, as we approach that 1, look at my average rate of change and how the slope of that line changes. That slope of the average rate of change, the slope of that secant line, eventually, as we get closer and closer to 1, that slope approaches the slope of the tangent, the instantaneous rate of change. And then once that point x gets to 1, you can see that the average rate of change actually is the same as the instantaneous rate of change right there. Oh, I passed it right there. So once that second point gets closer and closer as it approaches the point of tangency, that average rate of change will become the instantaneous rate of change. And let's look at that with limits, and let's define this, because these limits are going to be ridiculously common and very, very important. And here we are starting with the ordered pair 1, -3, That is one of the points. And my average rate of change is way over here at x, and I'm going to call that point x and f of x. Well, I'm going to start with my average rate of change, which I'm going to abbreviate AROC. Average rate of change is f of x minus my y coordinate here, which is -3, over x minus 1. And I want to analyze that. That's f of x plus 3. So here's my average rate of change. And I want to analyze that average rate of change as this x coordinate approaches 1. So we will look at that as x approaches 1. And the answer to that limit, when we solve that and work that out, the answer to that limit does give me the slope of the tangent. The only thing I have left to do to make this limit possible is replace the f of x with the equation that is f of x, and that is x squared minus 3x minus 1. So I could finish setting this up. Limit as x approaches 1, x squared minus 3x minus 1 plus 3 all over x minus 1, which then continues to reduce or clean up in the numerator to x squared minus 3x. -1 plus 3 is 2 all over x minus 1. And then you could go through factoring and canceling. You do synthetic division. There are ways you could finish solving that. I'm more interested in just the setup right now. So that's one way we could set up to find the instantaneous rate of change. We start with the average rate of change, move that second point closer to the point of tangency, and we could do it using the other method, the other naming method as well. This is the point. This is the point 1, -3. And instead of starting with this second point and calling this x, we're going to measure the distance between these two. So I'm going to call this distance right here h. And so if this point is x equals 1, this coordinate right here is 1 plus h. And the y coordinate would be f of 1 plus h. And we're going to do the exact same thing we did with this method on the left side, just the fraction is going to look a little bit different because I've defined my points. I've defined my interval slightly differently than I did on the left side. So my average rate of change is going to be f of 1 plus h minus -3, which is f of 1, all over change in x, 1 plus h minus 1, which will turn into f of 1 plus h plus 3. And that denominator becomes h. And that's my average rate of change. If I want the instantaneous rate of change, I need this point right here. I need the second point to get closer and closer to that point of tangency. And as that point on the right side moves closer to x equals 1, that distance h gets closer and closer and closer to 0. So this is the second method that we could use to find the instantaneous rate of change at a point, and the answer to that limit is going to give you whatever f prime of 1 is. So there are your two limit setups, and I wanted to show just kind of the structure, the meat of how we can take an average rate of change and apply a little bit of calculus with limits to turn the average rate of change into the instantaneous rate of change. And I'm going to pause the recording here and work out only the left side just to kind of see what answer I get and talk about how we know if our answers are reasonable. And I got -1 for my answer. That factored very cleanly. I got 1 minus 2 in the end, which is -1. And if you go back and look at the graph and look at what we did, we concluded that the slope of this green line is -1, and that looks really good to me. I feel very good about that answer. So if you know the shape of your graph and you know what it looks like, you can very frequently know if your instantaneous rates of change, if your numeric answer in the end is reasonable. And so there is an introduction to limits and average rates of change and how to turn those into instantaneous rates of change.